Well, okay. Well, let's see. Okay. So I mean, it's the same over here, right? 1, 2, 3 minus infinity dot dot dot. This is what we're actually talking about, the green functions, I guess, right? And 1, 2, 3. Because that GLL is E minus HL inverse. That's what we mean by that. And so here, I mean, this is a zero column. The matrix element, oh, we were doing GLD. I guess they're actually this one. So it would be the zero column and the first row. We're talking about this matrix element right there. The zero column and first row, row 1, column 0. And row 0, column 1. Those are the two matrix elements. T01 and T10. That couple the lead to the device, or the green function elements. These guys here. Right? You only have two matrix elements to couple the lead to the device. Because we're always going to set it up as a block tridiagonal matrix. The way we partition the matrix, it's always going to be block tridiagonal. So you'll have some block element, T10 or T01, that couples the lead to the device. Okay, so now we can the first algorithm we call the dumb iterative algorithm, because Khairul Alam had a comment in his code calling it the dumb iterative algorithm. We kind of like that. So ever since, it's been known as the dumb iterative algorithm. But it's incredibly robust and complex, and it's what was the adjective I used? It's incredibly robust and incredibly easy to code. So it's the first thing anyone ever does when they start coding up something. So we just said that let's consider, let's consider this system. So this is position. Here are my sites. This is site 0. We have to calculate the surface green function of my semi-infinite lead. Dot, dot, dot. Dot, 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 minus infinity. So there's my semi-infinite lead. And I've got, it's my usual tight binding. Everything is just an ideal crystal over here. I've got all my sites. My site energies are all identical. I've got my hopping elements between them. My T's, right? T, etc. So this is my left lead, ending at 0. So even though this is all the left lead, let's assume that site 0 is my, quote, device, just the way we did. So I have a device consisting of one node, rather like your homework, that's connected to the semi-infinite left lead, okay? And so, well, we just went through that. So the device consisting of one lead, my device green function, which is also my surface green function, is going to be equal to E minus H sub D of the device, which is now just like in your homework, just epsilon, right? Minus T0 minus 1 G surface minus 1 comma minus 1 T minus 1 comma 0, whole thing inverted. So since my device is one node connected to an infinite, semi-infinite lead, it's also a surface green function. Because there's nothing to the right, it's a surface, right? And this GS minus 1 is the surface green function if I set that T coupling minus 1 to 0 equal to 0. It would be the surface green function of my semi-infinite lead going from minus infinity to minus 1, right? Okay? Now, if I have a semi-infinite lead that goes to minus infinity to minus 1, or minus infinity to 0, do you think the surface green function is any different between those two leads?
No.
No. It's the same surface green function. So this is identical to GS00. And now you have a, depending on how you look at it, recursive equation. It's actually a quadratic equation. Closed form equation for our surface green function. So that's equal to E minus epsilon minus T 0 minus 1 GS 0 T minus 1 comma 0 inverse. I have a closed form expression for my surface green function.
So, like, is the logic behind the two Green's functions equal that since the lead is semi-infinite, so adding one node does not change the Green's function?
If I have a crystal, and whether there's an Avogadro's number of atoms back there or an Avogadro number plus 1, does it make any difference to the surface of the crystal? No, it doesn't. Right. So that's the logic. Yes, that is the logic. Okay, so that's great. I mean, if in our simple 1D type binding model, you can actually manipulate this into a quadratic equation for G, but in general, these would be block matrices, and so you can't do that. So, the general thing, what everyone does is solve this iteratively by having an initial guess for your surface green function and then iterating. So the thing that we iterate is this, GS. We put in this convergence factor, an I eta, E minus epsilon plus I eta minus T 0 minus 1 G S 0 T minus 1 comma 0, whole thing inverted. So the first thing we do is put in this convergence factor eta, an imaginary, small imaginary term there. And eta kind of depends on the problem and what you're doing. Eta, you can do a lot of things with eta, which we will talk about later. For now, you can just think of it as a convergence factor. And so it, values for eta, depending on what you want to do, range from 1 micro EV to up to, 20 MeV. A very wide range, depending on particular problems at hand and what you're trying to do with it. If it's only just a convergence factor and you really don't want any extra broadening, 1 micro EV. Much below a micro EV, it just gets lost in the numerical noise. That's what we found. So we said it's an iterative, so in any iteration, you need to start off your iteration with something. You need an initial guess. So the initial guess that kicks us off is you just put in G, S, and now the subscript will just be the iteration number. Okay, so the 0th iteration, you just put in E minus epsilon plus I eta inverse. That's your initial guess. And this I eta keeps the thing from blowing up on you in case epsilon happens to be equal to E. Keeps keeps the whole thing from blowing up on you. You don't have to be very careful about E and epsilon. That's one thing. And then you just substitute that into, this initial guess, you put it into that expression above it, and you just start iterating until the thing converges. You just keep feeding back, so, G, S, I, and that's your iteration number, is equal to E minus epsilon plus I eta minus T0 minus 1 GS, and this will iteration number I minus 1 T minus 1 comma 0, the whole thing inverse. So you just keep feeding whatever you got from the last iteration back into the next over and over again until nothing changes. You've reached some tolerance that you're happy with, right? Typical iteration approach, numerically. This thing converges pretty fast because if you start expanding it out, it converges as a continued fraction, and continued fractions have really nice convergence properties. So if you just start from here and substitute it into here and do that a couple of times, you'll see what you're really doing is that GSI is equal to 1 over E. I'll just combine the I eta into my epsilon, E minus epsilon, and just combine the t's together into a t squared, and then you have 1 over E minus epsilon tilde, and then minus t squared, and then again 1 over. So it's this continued fraction that each iteration, you're just building up this continued this continued fraction is what happened when you're back substituting this. And if you look up continued fractions, they have very, very nice convergence properties. They converge very quickly, and this is what this is doing. So the convergence is at worst linear with the number of iterations, and we generally find it to be faster than that. One way to view that is after each iteration, you're taking into effect one more site to the left, because the very first guess is just, this guess here for your 0th iteration is just the site energy plus some imaginary term. So you're not taking into account any connectivity to the left. It's just that site energy is 0. And then you take into account, the connectivity to the left on the next iteration here. So it's like one site to the left. And each time you can think of as adding the effect of another site to the left. So in that sense, it's sort of linear in the number of iterations. So if you have a unit cell length of 1/4 nanometer, 20 iterations takes into account 5 nanometer of lead. And usually, 100 iterations would be as much as you would ever need. This imaginary term, as I said, is a convergence factor. It keeps you off the real axis. But it also helps you converge in the sense that with this imaginary term, in some sense, these are really absorbing boundary conditions, because if you will see from another point of view, you're looking at, this green function is taking into account the response of everything to the left, but because of this imaginary term, if you put an imaginary term in your Hamiltonian, you get exponential decay. So it's sort of killing off the sensitivity of site 0 to what's happening 100 sites away because of this imaginary term in the Hamiltonian. Remember, we went through Schrodinger's equation with an imaginary potential, and it gives you this exponential decay of the wave function. So it's killing off the sensitivity of site 0 to any perturbation at site, a couple hundred away. So in that sense, it's an absorbing boundary condition. The dumb iterative method. So this is a dumb iterative. It's incredibly robust, incredibly simple, and not too bright. Dim. The dim method. All right. Okay, so as we said, this gives you, roughly speaking, linear convergence. Okay, and now another iterative algorithm is out there, which is harder to code, but it gives you exponential convergence. And it's called usually called decimation, a decimation algorithm. And sort of before we get into the details, the way this works is that you have this Hamiltonian of nearest neighbor coupling, okay, your site energies and your hopping term. And then in each iteration, the way a physicist would say it is that you integrate out every other site. And now you renormalize the coupling that goes from site n to site n plus 2. And you get these renormalized site energies and hopping elements. And so each hopping element now couples you from site n to site 2 sites away. And then you do it again. And now you're coupling from site n to site 4 sites away. And you do it again, and so your coupling is going as 2 to the n. So after n iterations, site 1 is coupling to site 2 to the n. And that's why it's an exponential algorithm. And so, very quickly, in 20 iterations, you're coupling from site 1 to site 2 to the 20th away. And so you don't need, that's more than enough, way more than enough. So we're going to take a look and see how this works. Let's see. Okay, so I guess, again, we're going to look at the left lead and write out a couple of equations that govern this surface green function that we're trying to calculate. So we have our E minus epsilon. Which one do I need? E minus epsilon, G0, G1, T. Okay, minus T. And then all zeros. Our usual minus T dagger, E minus epsilon, T, and since it's, the negative T, sorry, 0, dot, 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 and every row is going to look the same, just shifted over by 1, because it's this usual block tridiagonal form. These are, in general, block matrices. Minus T, etc. Acting on just G00, which is what we're after. G10. So this is the 0th column of the surface green function, which is the one we need. G20. All we really need is G00. I'll write one more column. G01. So we don't need any of this stuff. G11. G21. So there'd be a whole green function over here. I'm only writing 2 columns. And this is equal to our usual identity matrix. dot, 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 dot. We're just going to look at, I guess, maybe the first and second row, if that much. The equation resulting, let's look at the very first row. So I've got E minus epsilon acting on, and since I guess I'm just going to be looking at the zero row, let's see, row column, the 0th column. I'll just keep the row index, okay? I'll just keep the row index. Yeah, I'll just keep the row index. So E minus epsilon G0 minus T G1 is equal to 1. So that's the equation I get multiplying the first row of the matrix by the first column of the green function. So I'm just looking at this first column here. So taking this first column, multiplying by the first row, that's the equation I get. And now if I take that first column and multiply by the second row, I get negative T dagger G0 plus E minus epsilon G1 minus T G2 equals 0. And now what I'm going to do is, I said I want to get rid of every other node. So I'm going to solve for G1. So G1 is equal to G1 is equal to E minus epsilon inverse T dagger G0 plus same E minus epsilon inverse T G2. And so then we take this and substitute it back into the top equation. So I'm going to take this equation and put that back into there, and I'm going to get an equation relating G0 to G2 with some renormalized hopping elements and some renormalized site energies. So let's do that. So if I substitute that back in, I'm going to get a renormalized site energy, E minus epsilon minus T E minus epsilon inverse T dagger times G0 minus T E minus epsilon inverse T G2 is 1. So now you've seen how one step of this iteration works. Now I've got this new equation that looks like the equation we started with. I've got something acting on G0 and something coupling it to another site, but not G1 anymore. Now it's coupled to site G2. And I guess one thing I didn't mention is that, just to keep our sanity, the way I labeled these, so we're considering in this case the right lead, and my indices for the right lead start at 0 and go to infinity. And so we didn't have to use a bunch of negative indices just to keep it. So this is the way I wrote this matrix here. It's for the right lead, and I've set the indices of the right lead to go from 0 to infinity, just so we could not have to deal with negative indices, or indices like n plus 1, n plus 2, or etc. Okay. So we have what the physicists call renormalized our coupling, right? This is like a renormalized hopping element. It's now energy dependent. And this is a renormalized site energy. It's also energy dependent. And it looks, the renormalization looks just like a self-energy. It has that same form, and this is a form you're going to see over and over again. This is the self-energy on site 0 due to the coupling to site 1. This is self-energy on site 0 due to the coupling of site 1. It has the same form as the self-energy we just calculated for a semi-infinite lead, except now this quote surface green function is truly just E minus epsilon. Because it's an isolated site to site 1, which you have, as the physicists say, integrated out of the equation, is the way they express it. But whenever you do this, it always shows up in this kind of form, a T E minus epsilon inverse T. T E minus H inverse T, or T dagger. Okay, so we have renormalized it. Now we have something that's coupling site 0 to site 2. And we can, and so the way this algorithm is, you keep repeating that. Next time you'll have something coupling site 0 to site 4, etc., etc. Okay, now we're going to write out the equations of 2 consecutive rows of the matrix. Minus T dagger, G 2n minus 1 plus E minus epsilon G2n minus T G2n plus 1 is equal to 0, and minus T dagger G2n plus E minus epsilon G2n plus 1 minus T G2n plus 2 is also equal to 0. So these are some arbitrary 2 consecutive rows of the matrix, all coming out of column 0 of that green function. And so we're going to do the same trick. We're going to use the second equation to solve for this guy in terms of G2n and G2n plus 2. Okay, and we'll do that, and we get, so we get G2n plus 1. And it's going to look just like what we did before, E minus epsilon inverse, E minus epsilon inverse, T dagger, G2n plus E minus epsilon inverse times T 2m G2n plus 2. And all the rows of this equation that we generate by multiplying the first column of that green function by that matrix over here. So multiplying that column of the green function in red by that matrix, every equation generated from all those rows except the first one looks the same, except the indices are shifted by 1. Right? Every equation is going to be the same except the indices on the green function get shifted by 1. Which means I can just take this equation in green and shift all the indices and get an equation for G2n minus 1. Let me write that down. So G2n minus 1 is equal to, it's going to have the same form, E minus epsilon inverse T dagger G 2n minus 2 plus E minus epsilon inverse T G 2n. I just shifted the indices by 2. And now we take these two equations, the one in green and the one in purple, and we substitute them. We take these two guys and we substitute them back there. And so we're going to get rid of the 2n minus 1 and the 2n plus 1 and end up with a 2n plus 2 and a 2n minus 2, coupling 2n. And so if we do that, we're going to get something really long. Let's try, red is good. Minus T dagger, E minus epsilon inverse, T dagger, G 2n minus 2 plus this big renormalized site energy, E minus epsilon minus T dagger. So I get one renormal, this is for site 2n, and since I've, quote, integrated out site 2n plus 1 and 2n minus 1, I get a renormalization of self-energy term due to both the site on the left and the right. So T dagger, E minus epsilon inverse T minus T E minus epsilon inverse T dagger, all acting on G2n. And finally, coupling to site 2n plus 2 minus T E minus epsilon inverse T G 2n plus 2 equals 0. So we've integrated out, in general, every other site by doing this. So this gives a renormalized equation for G2n, and G2n is now coupled to G2n minus 2 and G2n plus 2. And the coupling is through these energy-dependent coupling elements that have this form of T E minus inverse T, or T dagger E minus inverse T dagger, or E minus epsilon inverse T dagger. And the on-site energy is also renormalized with, now you can think of it as two self-energies, just like our device coupled to the left and right lead, what you did in the homework, right? You just add the self-energies together, sigma L and sigma R. This is just these two terms here coupling to the left, to the site to the left and the site to the right. We pick up these energy-dependent, renormalization of the site energy due to this coupling. Right? They look just like self-energy terms. T E minus epsilon inverse T, or T dagger E minus epsilon inverse T. Okay, so now what? So we got to boil this down to an algorithm on how you would actually implement this. So at this point, you have what's called a renormalized Hamiltonian, corresponding to a chain of effective sites with a lattice constant of 2a. Effectively, your lattice constant is not twice as big. And so now you just renumber the sites, letting 2n go to n, and you repeat your procedure. Just renumber, let 2n go to n, and repeat. And you repeat and you repeat until you get convergence. So let's boil this down to an algorithm. So we need some initial quantities. So we're going to define some initial site energies as E0s is equal to epsilon minus I eta, and E0 is also an epsilon minus I eta. A0 is simply T, and B0 is T dagger. And then you iterate the renormalization of the site energies, these two guys, and the renormalization of the couplings, these two guys. So the site energies, the S is the one right at the surface, which is what's going to finally give you your surface green function. And I mean epsilon S, and the epsilon 0 is all the others. So we've got epsilon, or this E I, so this is my iteration number, EIS is equal to E I minus 1, EI minus 1S, plus A I minus 1. So again, these are iteration numbers. E minus the script E I minus 1 inverse B I minus 1. And EI, I mean, you can see this is a surface one since it only has one renormalization term, because the surface one is only going to couple to the site to the left of it, whereas all the other ones couple to a site both to the left and to the right. So these other generic ones in the middle of the lead somewhere are EI minus 1 plus A I minus 1 times E minus the script E I minus 1 inverse times a B I minus 1 B I minus 1 plus coupling to the other site. So those are the renormalization of my site energies, and then I have to renormalize my coupling, hopping elements, and the same thing for the B, just replacing A with B. Okay, so those are how we renormalize the site energies and the coupling elements in our effective Hamiltonian. And so each iteration, you basically are doubling your lattice constant. And so, as we said, after 20 iterations with a lattice constant of 1/4 of a nanometer, you've effectively coupled 1/4 of a millimeter away in one hopping element. Okay? In this iteration, you keep continuing this iteration until the AI and the BI, so you continue until the AI and the BI basically become negligible. There's no more coupling. And if there's no more coupling, it means you've renormalized site 0 to the point where you have the exact surface green function. In your effective Hamiltonian, you now have just one site that's not coupled to anything, and that's the one you need. You've renormalized that site energy, you've renormalized it until there is no coupling between that site. And so this effective, at that point, when that's true, then your G00, which is what you're after, right? Then G00 is just equal to E minus this EESI inverse. Because you have renormalized it to the point where you have one site that's just not coupled to anything. And it becomes very simple. So this is called the decimation algorithm, which is in all production codes, at least that we use. This is the way we calculate the surface green function. So we just did the right lead. This is for the right lead. Everything up to now is for the right. So is there any difference for the left lead? Is there anything that's different? So the only difference for the left lead is that, so in the left lead, this G0, our surface green function, is coupling to its neighbor to the left. And so the way we wrote the Hamiltonian, you couple to the left with T dagger, and you couple to the right with T. And thus, in the left lead, AI and BI, their role is reversed in the iteration algorithm of this surface site energy, epsilon I. That's the only thing, the only difference. So for the left lead, we have EIS is equal to EI minus 1 S plus B I minus 1 E minus E I minus 1 inverse A I minus 1. So I've just switched the role of A and B when I calculate this site energy for the surface site, and that's the only difference. The other expressions are the same. Right? So it's only this equation looks different. Is that right? Because in for the interior ones I have both terms coupling to the left and to the right. I have both an A and a B and an A term. So that's the only difference. So this is the decimation algorithm, and this is it's probably our method of choice. It's all these iteration algorithms are really robust. They seem to work even when the band structure is very funny or degenerate, or even when the density of states may be blowing up like at some kind of singularity, because you have an imaginary potential in there, and they're generally very robust. But it is an iterative algorithm. We do put an imaginary term on the diagonal to help convergence. And so there are other solutions to get this surface green function that are exact, and we generally refer to them as Modespace solutions. So up to now, everything has been iterative. And so let's look at some exact. So what we did in chapter 1 was an exact solution, right? We just came up with e to the I Ka over t as our surface green function. And let's do that right now. It's kind of a trivial example, but it's is an example of an exact solution. So going back to our simple 1D chain model that we did in chapter 1, if we look at the equation governing that green function of the left lead, we have minus t times g minus 1 comma 0 plus e minus epsilon g 0, 0 is equal to 1. Right? That would be the first row. I mean, g 0, 0 only couples to the next term to the left of it. So that's the equation from the first row for the surface green function of the left lead. And fortunately I wrote down, remember I wrote that, let's see, what am I referring to here? That's what I thought. So we wrote down that the exact green function for our 1D chain is G R I J is equal to I over gamma times e to the I Ka magnitude I minus J. This was our exact green function for our 1D tight binding chain. And we use this, and we use these sort of, so if I inject, say, at site J, then the response at site I is just given by this. I'm just picking up this phase factor as I move from J to I. And just like, when you solve Schrodinger's equation in some region where the potential is not varying, and but you have boundary conditions, you write the solution as the sum of the eigenstates of this, region where there's no potential variation. So if you have a box, you can write the eigenstate as the sum of the left moving wave and the right moving wave. These are the eigenstates of that flat region where there's no potential variation. And you sum them up and you get a, your standing wave, right? I mean, that's the way you solve Schrodinger's equation or any differential equation subject to boundary conditions. In this case, we say the response. So I have to do something about G negative 1, 0 to solve for G 0, 0. And G negative 1, 0, the physical meaning is what is the response of the system at negative 1 if I hit it at site 0. Well, that response is carried by the leftward, the way they say it is carried by the leftward moving wave. And let me just write down the answer. So G, the way I truncate this is using the fact that G minus 1, 0 is equal to e to the I Ka times G 0, 0. And if you look at that equation right above it, that's clearly true. And once I write down that, then, now I've truncated this equation up above, and I have the G 0, 0 is equal to E minus epsilon minus T e to the I Ka inverse. And if we make use of our dispersion relationship that E equal to, this is exactly what you did in your homework, E minus epsilon is equal to T e to the I Ka plus T e to the minus I Ka. And so you just use that fact so that this is equal to the inverse of, I guess, T e to the minus T e to the minus I Ka, right? So that's equal to e to the I Ka over T, which is our exact solution in this simple 1D chain model for G 0, 0. We didn't have to do anything iterative. We didn't turn it into a quadratic equation. We simply used what we knew that the response was propagating in this mode, and all it did to go from 0, 0 to 0, negative 1 was pick up this phase e to the I Ka. And using that information, knowing something about the way the response propagated being carried by the modes, we were able to truncate the equation exactly. So this is a trivial example of a mode space solution. Okay, so now we got to generalize that, because if it were that simple, we could all go home. But nothing worth doing is that simple, because it's already been done. So the modes or eigenstates of a periodic lattice psi m can be written as a block sum where n is your, if you think of layer indexes and something more complicated, or a site index with multiple orbitals per site. or unit cell index in general. So as you move each unit cell to the right or to the left, you're just going to pick up a phase factor, which will be different for each mode, raised to the nth power. So for example, this phase factor could be e to the I ka. Right? As I move one site to the left, it's e to the I 2k, e to the I k2a, e to the I k3a. So the phase factor, it looks just like when you replace e to the I, again for the EEs, my apologies, when you do a Z transform in going from a FFT to a Z transform. So this, you can just think of this Z as like e to the I ka times the periodic part of the wave function that just gets repeated, right? This is for some particular eigenstate. This is an eigenstate, periodic lattice. Just the general form of any eigenstate of your periodic lattice. So n is the atom index or unit cell index, whatever the periodic thing is that you're repeating. And Zm is your propagation factor. And you can just think of it as e to the I ka for a propagating state. We'll see later when we really start using this, the k could be complex because we may be in a region in the band gap, for example. K does not have to be real anymore when we start really using this. Zm is your propagation factor, n is your atom or unit cell index, whatever the periodic unit is being repeated. And this periodic thing is a linear combination of your atomic orbitals. So chi m is equal to some, say we're using a sp3 basis, so you've got like 4 orbitals and say it's periodic for each atom. So it would just be some sum of your 4 basis states of some amplitude corresponding to the particular mode, Cmj, alpha j. Okay, so it's just in your sp3 basis, some for whatever eigen, like if this were your, your valence band, it would just be your linear combination of p orbitals, or your conduction band, your antibonding s orbitals, or something like that. Whatever gets repeated, the periodic part of the wave function. And now we insert this expression into the eigenvalue equation. So we're going to insert this into our eigenvalue equation, h minus e psi equals 0. And in general, we have this layered form with nearest layer coupling, nearest neighbor coupling. And so it's going to look like t 0, -1 for a particular mode, chi sub m, z m minus 1 plus the diagonal block, which I'm calling d0 minus e chi m plus t01 chi m zm equals 0. And in general, these matrix elements, say for example, we're using our sp3 basis. Right? So in that case, all these matrix elements would be 4 by 4. And your chi's would be a column vector of 1 by 4. Yeah, let me just come to 3 more equations and we're done. So we multiply through by Zm, and we get T0 minus 1 chi m plus D0 minus E chi m Zm plus T01 chi m Zm squared equals 0. All I did was multiply through the whole thing. And that looks like, so the Z's are unknown. We don't know what the Z is. We don't know what the chi is. Okay, these are something we need to solve for. And you know, Z, it looks like a quadratic equation in Z, which is not good. But you rearrange it like this. So you rearrange it as T0 minus 1, 0, times the vector, or the column chi, Z chi, plus Z times D0 minus E T0 comma 1 chi Z chi equals 0. So I've just rearranged the equation. If you multiply that out, you'll see you get the equation right above it. Multiply those column vectors by those row vectors, you just get the equation right above it. And now we, to turn this into a generalized eigenvalue equation, which was what we need, we had a trivial second row to this to turn it into a generalized eigenvalue equation, which looks like this. So I have T0, negative 1, 0, 0, negative 1, plus Z times the matrix D0 minus E 1 T01 0 acting on my column vector chi Z chi equals 0. And this is a generalized eigenvalue equation for Z. And the eigen, so you've got, this is my generalized eigenvalue, Z, and this is my generalized eigenvector. So we've turned this quadratic equation into a linear equation in Z by doubling its size. The column vector is twice the size. All we're looking for is chi, so when numerically you solve this, you actually just throw away the bottom half of that column vector, because all you're looking for is chi. So by doubling the size of the matrix, you've turned it into a linear equation. This is what's called a generalized eigenvalue equation. Generalized eigenvalue equation. It's you know, you look it up in MATLAB. You can solve it with the Eig function. You just give it two matrices, A and B. Just look in the manual, Eig, and it automatically gives you a generalized eigenvalue solution. And I can't remember. I don't think I wrote it down here. You know, so you see these two matrices in here. One is A, one is B, and you know, usually this is written as lambda, your generalized eigenvalue. So it's like A plus lambda B acting on, you know, the vector equals 0. If you look up in the MATLAB. And so this is what we solved to get these modes and these propagation constants Z. And from these, we use these to truncate our system of equations to get the surface green function. And I guess we're going to have to pick it up here next week, next Monday. I'm off to Washington for another week. I don't get back till Friday night. So I'll post some homework on iLearn just to give you something to think about. Basically, I guess the rest of those problems at the end of chapter 1. Yeah, we'll see. See how far you get. We can discuss them next Monday and see if there's any issues. So, okay, send me your homework, please. And I'll see you next Monday.